Good morning, good afternoon, or good evening, depending on where you're joining us from today. Welcome to SmartBear Connect 2020. My name is Robert Schneider. I'm a partner here at WiseClouds in Silicon Valley. And over the next few minutes, I'm going to be talking to you about some of the most common API and microservice performance testing challenges that we've seen. WiseClouds is a specialized training and consulting company based in Silicon Valley. We are big believers in the Ready API product and have been delivering classes on it since 2007. We continue to use it each day as part of our professional services in designing, developing, and testing APIs and microservices. A little bit about me. I have more than 20 years of experience in all sorts of distributed computing topics, from databases to microservices and APIs and everything in between. I've written a bunch of books on these topics, and I continue to speak at various industry events all around the world talking about these topics, which are of great interest to me. If you'd like to learn more about what I specialize in, you can look at my blog at rdschneider.com. Before I get started, I want to thank SmartBear for pulling this event together so quickly during what are unprecedented, difficult times for all of us. I also hope that all the people watching this event are staying safe and managing during these challenging times. Let's get the ball rolling by learning about what happens when you don't test your business processes as holistic units of work, but instead focus on testing single individual API endpoints. If you look at an open API or other definition for an API or set of related microservices, what you'll notice is that these resources are frequently composed of a collection of specialized functions. Other names for these assets are methods, resources, and so on. Yet no matter what you call it, each individual resource serves a particular purpose. In an e-commerce system, one function might be responsible for establishing a connection, another for searching for an item in inventory, and yet another for adding that item into a shopping cart. An enterprise-grade API may have dozens to hundreds of these unique resources. Developers create applications that orchestrate these functions to carry out a series of units of work. One typical unit of work would be logging in, searching for a product, adding it to a shopping cart, paying for it, and then receiving an email confirmation. That example I provided might break down to 10 API calls. Yet what typically happens is that when examining that API for performance, the testers will merely invoke each individual API endpoint without considering the role that it plays in larger business processes. The idea is to bombard it with traffic to see where it falls over. And that's a good thing to know, and it should absolutely be part of a performance testing strategy. However, it doesn't do anything to consider how the specific API endpoint is likely to be invoked in the context of the applications it was written to support. And remember that a given method will routinely be a participant in dozens of business processes. It's understandable why you might want to simply focus on transmitting huge amounts of load to your individual API endpoints. After all, that will certainly shine a light on performance challenges and thus let you take corrective action. So if that's how you're operating now, by all means continue to make that part of your test plan. But don't lose sight of the fact that APIs almost never operate in isolation. Instead, they're routinely going to be utilized in support of many different business processes. Unfortunately, plenty of organizations outsource their performance testing of their APIs to external professional services providers. In most cases, these third parties don't know a lot about the business processes of their customer. And naturally, this means that they're not going to understand the site-specific purposes of the APIs that they're going to performance test. If you think about your own organization and its APIs, imagine how many nuances your environment is likely to have. For example, in your API collection, it's quite likely that you'll have hotspots, individual resources that are called all the time. Security-oriented endpoints are a great example of these types of hotspot. On the other hand, there may be methods that are invoked only a few times a day, or you may see sets of API calls that are closely linked together, such as a header detail group of methods. If you configure your performance test to merely exercise each endpoint by itself, without thinking of its role in the overall bigger picture, there's a high likelihood that your users are going to find a performance problem at the least convenient time, when your APIs are in production and your phone rings at 2 a.m. Fortunately, there's a straightforward path to eliminate this risk. First, it's still a very good idea to place fine-grained endpoints under load. If that's what you're doing already, carry on with it. And if you're not keeping track of the statistics generated during these tests, try to incorporate that into your testing process. But moving forward, you should really attempt to gain a better understanding of how your APIs will really be utilized. There are lots of ways to attain this goal. For example, if your APIs are employed in a user-facing application, you might want to sit alongside your users to see how they interact with the system, and by extension, the APIs. On the other hand, if your APIs are primarily invoked in support of machine-to-machine processes, consider scoping their activity using the HTTP monitor that's embedded with Ready API, or a third-party tool such as Fiddler. These will give you unparalleled insight into how you should replicate the real-world activities in your load tests. And if your APIs aren't yet ready for production, spend time with the users and developers to at least gain some knowledge into how they expect things to go. Whether you're performance testing brand new APIs or evaluating ones that have been in production for years, don't overlook the powerful scenario capabilities that you'll find in LoadUI. These let you assemble individual functional tests, represented as test cases, into much larger workflows. You have a great deal of control over how these workflows then proceed. You're free to allocate load ratios among them, incorporate looping, and configure many other behaviors that will help your performance tests model how your APIs will truly be employed. Hard coding data is a really common flaw in many functional tests, but it becomes quite deadly when you start applying it to performance tests. Let's take a look and see what happens when you do just that. Through my work at WiseClouds and elsewhere, over the years I've lost track of how many web services, REST APIs, and other distributed computing assets I've had the opportunity to learn about. Yet no matter how diverse these resources have been, one constant remains. It's quite rare to encounter an organization that builds out a comprehensive library of functional tests that are driven by large, meaningful data sets. These shortfalls are quite understandable. These enterprises are fast-moving, their APIs are in constant flux, and there certainly isn't enough time to develop the kind of collection of functional tests and associated pools of diverse data that would truly exercise these APIs. Yet despite how uncommon it is to find an organization that's fully committed to dynamic data-driven tests, it's even more unprecedented to run across one that takes their functional tests and uses them as the baselines for their API load tests. In fact, API performance testing itself is frustratingly rare, never mind using dynamic, data-driven functional tests as their foundation. What's far more likely is that an API performance testing team will end up reusing the same handful of hard-coded examples to drive their load tests. It's even possible to run across a group that fires off a single static message hundreds of thousands of times to their APIs. Again, this isn't because of laziness or sloppiness. It's just that developing these kinds of robust functional tests can be difficult, and then using them under load even more so. The problem can be magnified in an agile environment where builds are happening multiple times a day. You might be wondering, what's the big deal about sending the same hard-coded message to the API hundreds of times per second? After all, you'll be able to measure the maximum, minimum, and average latencies for all these communications. You'll soon identify hotspots, performance degradation, and outright crashes. Armed with this information, you can confidently go to your developers and tell them all about your troubles. And that's mostly true. However, here's another way to look at it. Most APIs eventually interact with some sort of data repository. That information store could be a traditional relational database, a NoSQL product, something in the cloud, or even something as mundane as a flat file or a spreadsheet. Realistically, though, for most enterprise-grade applications and APIs, it's going to be something big and powerful with lots of memory and processor power supporting it. What happens when you keep asking a powerful database platform for the same response over and over again? Since it keeps getting polled for the same data, the server will store the result in memory rather than fetching it from a physical hard drive. Or even if it's using solid-state memory drives, the same response will end up cached in the absolute fastest storage possible. In this circumstance, your results will be coming back to you incredibly fast. It'll seem like the APIs are operating at the speed of light. Of course, once you switch to production usage patterns, there will be a sudden, mysterious drop in performance. Not good. On the other hand, what if some sort of updating is going on in the backend data repository? In that scenario, there will be enormous contention problems as hundreds or thousands of concurrent virtual users all try to smash their updates into the same record. At best, your results will be far slower than you can really expect. At worst, you'll end up with an enormous number of errors that will not endear you to your developers or operations colleagues. Here's another example, and you'll see this repeated elsewhere in my presentation, about how a collection of thoughtfully designed functional tests are the foundation for robust API and microservice performance testing. If you establish this baseline, you'll find it helpful in all sorts of situations. In terms of data-driven load testing, you should begin by understanding the business processes that your APIs represent. Armed with that knowledge, you're in a great position to start writing functional tests that mimic these procedures. And once you know that, you can then incorporate meaningful, accurate data, and lots of it, into your functional tests. Don't forget that SoapUI has some very potent data generation features that take the tedium out of feeding your tests with data. In fact, you can blend machine-generated test data provided by the data generator data source with more relevant information that you provide. For example, you could use SoapUI to generate random email addresses, phone numbers, postal codes, and so on, while you supply customer names, account numbers, and such. Here's also where you can think about associating dynamic assertions with your data-driven functional tests. Why not take advantage of these safety checks, even in the context of performance testing? Once all of this has been done, it's actually a very simple matter to develop solid performance tests on that foundation. All you need to do is use your test cases to design your scenarios in LoadUI. If those test cases already use dynamic data and assertions, all of that work will carry forward to your performance testing. Coming up with an accurate and meaningful number of virtual users can be quite difficult. Let's see what happens when you fail to come up with these realistic numbers. To conduct a performance test for your API or microservice, you'll first need to determine how they'll be utilized by the outside world. If your APIs are meant for human consumption, whether directly or more likely front-ended by some sort of GUI, you'll be setting up a certain number of virtual users to represent this community. In Ready API, these are known as VUs. In other software packages, they're also known as threads. On the other hand, if your APIs or microservices are being invoked by other processes without people in the mix, you'll likely be configuring a rate to simulate a constant stream of arriving traffic. In either case, you'll do your best to establish values that reflect what your API or microservice will encounter once they're placed into production. In theory, that's how it's supposed to work. Sadly, what ends up happening in reality is that developers and even business users have a very difficult time coming up with these numbers. This shortfall isn't because they haven't put a lot of thought into the APIs. It's more likely a reflection that, in the case of a new application anyway, that it's just not possible to predict accurate usage metrics. If you keep asking them the same question, you'll keep getting the same shrugged shoulders. So what's a tester to do in a situation like this? As is usually the case when confronting great uncertainty, people tend to make a best estimate about what this number should be and then proceed using that value. With the passage of time, it's even possible that the testers will forget how they even arrived at the number of VUs or incoming rate. Guesswork is never a good thing when designing applications, but it's particularly dangerous when attempting to test APIs or microservices. And performance testing is the place where it's the riskiest. Users can get very creative when coming up with their expected load numbers. Sometimes it's because they're overly optimistic. You might be launching a new product offering that uses microservices to get its work done. The business analysts swear that this new system will be a huge success on day one. The flip side is that your new application may be designed with very modest usage goals, yet for some reason that you find that it's more popular than you expected. My experience over the years has been that it's nearly impossible to come up with accurate usage values for a new system. It's a lot easier when the application has been in production for some time. In fact, you can routinely extract forensic metrics from your application hosting infrastructure to give you precise usage patterns, which you can then incorporate into your API performance tests. But for new applications, consider the ramifications if you under-provision the server-side resources that support your APIs. You were told to expect 10,000 users per minute, yet the true number is 50,000. As soon as these new APIs are placed into production, there will be all sorts of excitement and scrambling to acquire additional assets to support the higher user count. And that's assuming that extra resources are even available to place into service. On the other hand, suppose that you were told to expect 50,000 concurrent users a minute. You set up your tests for that number, yet you only receive a fraction of that volume. Performance will be great, but your organization might be spending a small fortune on unnecessary resources. So here's a scenario where there's not a whole lot you can do to get realistic user counts from the users themselves if they're not able to provide it with you. It's not a question of good faith or bad faith. They may not know. So certainly you want to ask them and talk to multiple constituencies to get their take. But since you're not really going to know, why not start up your performance tests, first of all, using lots of different scenarios, but also being sure to ramp up your user counts, your virtual users or your arriving virtual processes, starting at a very low number and then slowly ramping them up. Whatever that ratio is up to you. But at the end of the day, what you will have done is shown where your APIs hit the wall. And you can confidently go back to the business users and say, well, everything looked great from one virtual user all the way up to 1,000 virtual users, but between 1,001 virtual users and 1,500 virtual users, we started to see a degradation, and above 2,000 virtual users, we have a real problem. So at least you've educated your users about where they have exposure. Most APIs are invoked from a variety of geographical locations, yet it's quite common for them to be load tested from a single location, often in the same data center as where the backend resources are running. APIs and microservices are meant to allow distributed access to your computing resources. That's their primary reason for existence. Where does this access come from? Well, if their main audience is internal users or machine-to-machine processes, the traffic will likely be arriving via your organization's wide area network, or WAN. On the other hand, if the APIs and microservices are meant for public consumption, and that includes external partners, customers, and so on, then the traffic will be coming from outside your network. Even if the APIs are designed solely for internal usage, there's still a high likelihood that they'll be serving users from outside the location where these resources are running. In other words, if your organization has multiple locations, then the traffic to your APIs will be arriving from elsewhere. And if your APIs service an external audience, then you can expect inbound traffic to be coming from anywhere in the world. Yet despite this geographical diversity, plenty of API performance testers opt to generate and transmit their load traffic from a single location. This might be found within either the same physical data center or the same cloud region if that's their architecture instead. In other words, geographic distribution is not factored in to how the load volumes are being created, transmitted, and reported on. While this type of performance testing is easy to carry out and straightforward to do, you are completely losing what kind of network latency you can expect to encounter when the application or the API makes it into the real world. So you might think we have a really well-performing API here. You suddenly incorporate real-world users who are coming in from thousands of kilometers away, and you now have what appears to be a very poor performing API, and now you have to react. You have to start thinking about adding additional resources, maybe using a content delivery network, whatever it might be. Your SLAs could be put in jeopardy. All these bad things can happen because you did not factor in network traffic time. Networks are fast, but they are not infinitely fast, so you have a risk here if you don't incorporate distributed testing. Unlike many of the other problems I'm describing in this presentation, this one is actually quite easy to solve, especially if you're proactive and plan ahead. There are all sorts of different options to generate load from distant sources and then transmit it to your APIs. You can find solutions from SmartBear itself, third-party cloud providers such as Amazon Web Services and Microsoft Azure, and other specialized vendors. If you're so inclined, you can even stand up your own load generation agents and create distributed traffic from them. Each of the options I just listed are affordable and pretty straightforward to implement. The key here is to be thinking about this from the very beginning of your initiative and to build it into your test plans. When you're designing an API performance test, one of the most critical considerations is to envision how many virtual users or arriving inbound processes you'll be simulating. At the same time, ideally you should be planning on how you'll be creating that load and where it will come from. Here's yet another instance where deep knowledge about your APIs will come in handy. For example, if you're expecting lots of traffic from Europe to your US-based APIs, then be sure to allocate sufficient load generation from those sources. On the other hand, you can underweight load generation from geographies that you don't expect to create significant traffic. Whatever you decide, make sure that you keep track of the metrics from each of your load agents, including, of course, where they're located. This will let you definitively state whether distance from the APIs plays a major role or not in your anticipated performance. Lots of APIs orchestrate other APIs as part of their operational procedures. So it's really important whenever possible to include those external APIs when conducting performance tests. APIs and microservices are the core foundation of distributed computing applications. That means that the overall software logic is assembled or composed from individual units of specialized code that comprise the APIs. Many applications utilize a single API, but many others make use of external APIs to get their work done. Sometimes these external APIs and microservices are developed within the same organization. In theory, this means that they should easily be accessible as part of the software testing process. In other cases, however, the overall software solution relies on APIs that are developed and owned by third parties. These external entities may be government bodies, partners, customers, or a host of other organizations. What they all have in common is that they may be unwilling or unable to grant access to your testing process. It could be that they don't offer a dedicated sandbox, or their live APIs kick off downstream processes. Maybe they expect to get paid when you invoke their resources, or their APIs may not be ready or are riddled with bugs. Regardless of the exact reason, you don't always have the option to include external APIs during your own performance testing process. Failing to account for external APIs and microservices is a big problem throughout the testing lifecycle. Let's begin with the functional side of testing. If you don't have access to these outside resources, you can only guess how your applications will behave when needing to invoke them. Carrying that shortfall forward to load test only makes things worse. Now you don't know, number one, how your APIs will act in concert with the third-party APIs, and number two, what kind of events will crop up when you start placing the whole assembly under load. If you wait to place the entire application, including external APIs, under load, you're subjecting your users to a big bet. They may learn, too late, that the architecture isn't really going to deliver on the responsiveness that they were promised. You'll then be under the gun to correct the problem if that's even possible. For example, you may have to go to the third party, point out the issue, and ask them to dedicate more resources to deliver the kind of performance you were expecting. As you can imagine, this might lead to all sorts of unpleasantness, ranging from finger pointing to even worse. Here's a great example of how resolving a potential performance risk can entail a set of both business and technically related steps. First, you should approach the entity that offers the external API and respectfully request access to a sandboxed version of their resources. Nowadays, this is quite common, and they very well may be able to address your inquiry. As part of this conversation, you should find out how much load they're willing to let you place on their sandbox version. If they don't have a sandbox yet, you may be able to persuade them to create one for you. If all that fails, then it's up to you to come up with a reasonable facsimile of their APIs. I'm happy to report that there are some superb virtualization products on the market. SmartBear's Service V is a great example of one of these solutions. We have customers using it to create incredibly sophisticated virtualized APIs. You can dial up or down the virtualized API's bandwidth, server-side latency, customize response messages using dynamic data, have it throw errors, and so on. I've been very impressed with Service V, so be sure to explore it for your own environment, even if you don't make use of external APIs. After all, it's very useful anytime you need to work with an API that's not yet readily available. APIs were originally designed for machine-to-machine interaction, but increasing numbers of applications front-end those APIs with GUIs such as mobile devices or browsers. Let's see what happens when you don't incorporate those front ends into your load testing. When they were first introduced, APIs were mainly intended for machines to communicate with other machines. They generally weren't meant for human beings to interact with backend resources. But over the years, APIs and then microservices proved to be very valuable assets that could serve multiple purposes. So what's ended up taking place is that nowadays, a great many applications are designed with GUIs, whether in a web browser or in a mobile device app, that basically front-end the exact same microservices that are being used for other purposes, such as machine-to-machine communications. But here's the thing. Those GUI layers incorporate a tremendous amount of interwoven security, authentication, and other validation logic. If you're trying to write functional tests via these front-end components, you can use tools such as SmartBear's Test Complete to carry out behavioral evaluations that preserve the GUI experience. But those products were never really meant for the kinds of massive load generation tests that are necessary to perform regardless of the application's presentation layer. If you want to write powerful performance tests that fully exercise the back-end logic in the API or microservices, it can be tempting to bypass the GUI layers and directly invoke these assets. Unfortunately, trying to create tests that incorporate the security and authorization checks directly in a tool such as Loadul is an extremely difficult challenge. It's hard enough for a single user. Attempting to do it for tens of thousands of virtual users can be nearly impossible. So when faced with this kind of problem, it's very common to think about maybe just completely ignoring or bypassing the GUI security aspect of your application, hard coding something, turning off security validation. All these things are potential workarounds for that, or maybe writing all the code yourself. So first, if you omit this security testing, you are omitting potentially a major performance bottleneck, and once again going to your users and giving them a false sense of security about what this application will perform like in the real world. On the other hand, if you try to write a lot of this code yourself, it's going to take you away from your core job responsibilities, and frankly, unless you're really investing a lot of time and are really good at this and understand it, you're going to do a poor job of replicating or of emulating what that browser-based security is doing. The first step in arriving at a solution to this problem is recognizing that every tool has a specific purpose. So, for example, Ready API is ideal for doing functional and performance security and virtualization on APIs, but it is not meant to be a GUI-based testing tool. For something like that, you really want to be looking at specialized products such as Load Ninja. That product is meant for driving load through GUIs. What I'm suggesting basically is that you use both products in your performance testing process. For the GUI-based load generation, use Load Ninja. For the API-based, the backend API-based aspect of your performance tests, use the functional test library that hopefully you've built up in Ready API, and then apply that to performance tests that are distributed and so on. And then with those two factors, the GUI-based and the API-based, you have a much more comprehensive view of what you can expect once your applications go live. Each API faces a different performance profile, and in recognition of that, SmartBear included all sorts of different load generation scenarios in LoadUI and Ready API. Yet, far too many users, when conducting performance tests, only look at the fixed load generation scenario. LoadUI Pro offers 7 different ways to generate the transaction volume to drive your API performance tests. Each of these load generation scenarios was carefully designed to simulate how traffic, in the form of virtual users or arriving processes, will reach your resources. You can even write your own entirely customized load generation scenario if you feel that none of the already provided templates works for you. Yet surprisingly, many LoadUI users just stick with a default fixed load scenario. In this case, Ready API will spin up as many virtual users or arriving processes as you stipulate, and it will keep them active at the same level throughout the duration of the test. This holds true whether you specify 1, 10, 100, or 1,000 of them. I suspect that the reason for this is that users simply overlook all of the potential variety at their disposal when it comes to generating load. The path of least resistance is what they end up following, and that's unfortunate because they miss out on some really interesting alternative takes. Now you might be thinking, well, the business users told us we can expect 10,000 active users at any given point in time, so what's the problem with using a fixed number of virtual users set at 10,000? And it may not be a problem, but imagine that these users come in, you average 10,000, but maybe they come in huge bursts of usage, then things get quiet, whatever it might be, or maybe it's not that. If you're not understanding your true load patterns and you're not testing true load patterns, you might be under provisioning or over provisioning based on what you think is going to happen, but because you've used a fixed value, you never really see any kind of variability. And this variability might be actually what your application will be experiencing once it is placed into production. Fortunately, it's easy to apply a good solution to this problem. As you can see on the screen, there are 6 other different types of load scenarios, so why not use each one of them? Try it out, experiment, if for no other reason than to simply calibrate your load test. Try it with ramp ups, try it with ramp downs, try it with randomization, do it with fixed, whatever it might be. These are all good indicators about how your APIs can adapt to multiple different types of traffic patterns once they are placed into production. But remember, if you're going to go this route, and I recommend that you do that, keep track of your individual test runs. So you could say, at this date and at this time, I ran this load generation profile. Here's what my responses look like. Here's the average. Here's the max. Here's the min, whatever it might be. And now you know different types of profiles that you can go back to your developers and explain to them what kind of load results they can expect once the application reaches production. Okay, there you have it. Those are 7 of the most common API performance testing problems that I've seen over the years. I hope that you found this information useful, that you found ways that you might be able to apply it in your own environments. I'm always happy to talk to people about their individual experiences. I find it really fascinating to see the diversity of APIs that are out there and how people are making them ready for production and making their users happy. So if you'd like to reach out to me, my contact information is there on the screen. Please feel free to connect with me. I'd be happy to learn more about what it is you're doing. And thanks again to SmartBear for hosting this virtual event, and I look forward to seeing you all in Boston in 2021. Take care.